Hi everyone, welcome to our final project presentation. My name is Yuanzhong Pan and this is done with Yibo Zhang. The first step is autocomplete. What we did is we take the input name and then transfer them all to lower cases. Then we traverse all the data points and find those with name and transfer those names to lower cases and store them in a new string. Then we substring this name to the length of the input and compare it compare if it's same with the input name in lower cases. So if it's equal, we just push the original, which is now transformed to lower cases, into the result vector. So here we had two examples. If we put RA, we have Ralph, then Rens is 29, and Ramen. And if we put TRO, which is mixed cases, and we still can have the correct results. So step 2, it's pretty straightforward. So we just traverse through the data, and if the name matches, we just put the latitude and longitude into the result vector. So this is the example of CVS. Then this is the example of Choi View swimming pool. They uploaded in the map. And then we did calculate shortest path. We tried two different algorithms, the Dijkstra and Bellman-Ford. In Bellman-Ford, we tried to use a non-recursive implementation and to see how it works. And the results are here. We tried this. Here's some examples. So from Ralph to Chick-fil-A, Dijkstra spends like 1 million. And we noticed that Bellman-Ford, in a non-recursive way, it spends quite a long time. This is also true for another example and the third example. So we observed that they always return the same path, which is the shortest path. But Bellman-Ford takes longer time. The total time is similar for the 3 cases. So this is a problem of our non-recursive implementation. So I guess we need to improve our code to avoid like traverse through all the nodes. So this need to be improved. And this is the observation for that. And step 4, traveling Trojan, we use the backtrack, and to opt, we didn't have time to do the brute force yet. This is gonna be appended after this. So what we found is they can both give out solve the traveling salesman problem. And so when we increase the number of places, so if we take 5 places, the time of the 2 algorithms are similar. But if we take 10, we find that for backtracking, it's like 1,000 times more. But 2OPT gives only like a 10-fold. And if we go to 15, there's another 1,000 time time increase for backtracking, but only like 3 times of 2OPT. So we find that 2OPT can significantly change the running time as n goes larger, and the end miles are actually comparable to each other. And step 5, circuit detection. Here, how we did it was traverse through all the nodes and put those in the squares. Put those nodes in the square to a visited map. For time-wise, I'm gonna skip this, but the results are, so this is first example of there are no cycles in here. It gave us false. The runtime is 200,000 microseconds. And then we did a larger circle, and then we did a similar circle, but switch it to another place. Here, the observation is the square in 2 examples are comparable, but the first one have smaller runtime. This is because when we do the DFS, we actually in here we didn't only plot the circle, we also plot the path to find the circle. So this is a DFS. we kind of implement it in a recursive way. So it kind of goes deeper and deeper until it finds a circle instead of finding the first cycle in the first node. So this may cause a longer runtime. It's an interesting observation of us. And this step 6, the deliver Trojan, here's how we did it. And then we had some examples. This takes 23 microseconds. And this is a linear example, which takes 22. This is a more complicated example, which takes 300 microliters. But and we can detect a cycle in our algorithm. So if we find a circle, the program will break. So second one, the 7th one is also more straightforward, which is calculate the distance using backtracking and then find the ID. Here's some examples of finding routes: 5 nearest neighbor of routes, 7 of Expo Vermont station, and 9 of Tommy Trojan. So thank you. This is our presentation.